Okay, now we're recording and we have everything working the way it's supposed to. Files are in the wrong places, and when I save this, I don't know where it's going to be. Those are minor things. Homework questions. Anyone have a question or two on homework that we can look at? Or yes, Raquel. Right.
Our box number. Where do we pick up that stuff?
There's nothing returned yet, but it's just on the other side of this wall.
Okay. Mine is like 102, and it only goes up to like 50 or something.
Well, yeah, the one is assumed. Carmen was the first one with her hand up.
So if we turn in our homework at 5 o'clock,
yeah.
Where is that due?
My office, which as you saw me walk to just a second ago, is right there. Okay. Casey.
2 questions. One unrelated to the assignment. If I wrote on printer paper, is that like acceptable?
Yeah.
Okay. There's also 3 different colors of ink, but the work is right.
I'll work with it.
Okay. And question number 2 would be, well, on my paper it's number 6. It's the one about that one.
The different materials?
Yeah.
Okay.
But it's definitely a different question, like on the old one.
The wording is different, and part B is different. Part A is the same, just slightly different wording. Part B is actually different because, we copied the wrong thing. So, let's look at that. That way there won't be any confusion. So, different materials, A, B, C, and D, rest on a table. Rank the materials from greatest to least by how much they resist being put into motion. What do we call the property a material has of its resistance to change in motion?
Friction.
Not friction. Inertia. Inertia is the name for the property of something resists change in motion. And Newton's first law, the law of inertia, says that an object stays in constant motion unless acted on by a force. Second law says the acceleration is the net force acting on it divided by the mass. Mass is our measurement of inertia. So if it asks for which one resists change in motion the most, that could be paraphrased as which one has the largest
mass. Yes.
Inertia, which means mass. We measure the inertia in mass. Yeah, I want to make sure you know you're right.
So I'm right, but I need to know why.
Yeah, exactly. We're in physics. Well, we're not in physics. We're in physical science to understand why things work. So we're just asking to rank them in order of mass. So which one has the most mass? Actually, it's from greatest to least. Yeah, so we'd go 15 is bigger than 12 is bigger than 10 is bigger than 2. Oh. So then we have, and remember, you do need to give your reason. If you just answer with the words that Casey said, B, A, C, D, that's not sufficient. Well, it's sufficient for 1 point. But you have to say, mass is a measurement of inertia, so ranking them from greatest to least mass gives me this. 2 questions. This is about this question, right?
It's about,
Okay,
so, like on this one, and all of them, we have to say because on all
on everything. Yes, okay. On all homework.
Like it's number
Tiffany,
1.
right? No? Uh-oh.
Close.
It starts with C then.
Yeah.
Candace, again. Shoot.
Like number 1, how would we explain our answer like that?
As soon as I finish this, ask me. Okay, I want to finish out this problem, and then I'll look at that to answer. Right, you said number 1, like problem 1 up here, right? Yeah. Okay, so then there's the second part, and that's the one that's actually different from what it originally said. And so we're all here, but 2, we can clarify and just be done with it. Rank the materials from greatest to least by how much support force, also known as normal force, that was one of the questions that did not get randomly chosen for the quiz, the table exerts on them. So what is the definition of the support force or the normal force?
Was that the question I was thinking?
I feel like that's reworded.
It is reworded. That's what I just said.
Is it the same concept?
No, the other one was something about stopping.
Oh, I still didn't get that one either. So.
But let's get this one, and then we'll be good.
All right.
So what is the purpose of the support force?
The opposite force of gravity.
Sometimes it is, sometimes it's not.
Not the one that's perpendicular to the
It's the one that's Tiffany. It's the one that's perpendicular to the surface to keep the object from going into the surface. Friction is parallel to the surface. Normal force is perpendicular. And so in this case, what Brittany said is correct. It's opposite to gravity because what's trying to push each of those objects into the surface? It's gravity. Remember my example from class? If I'm pushing on the wall here, what direction is the normal force? It's coming out to keep me from penetrating. Has nothing to do with gravity. Right? So you have to look at what's pushing into the surface. And in this case, Brittany was right. It's the force of gravity that's pushing in. And so the support force is going to be whatever is necessary to keep it from coming in.
So would that mean that the order's still the same?
That would mean the order's still the same.
All right.
Because the most massive one is the heaviest, which means it's going to have the biggest support force. Now, if I was pushing down on one of them, that would make it bigger, right? That's not gravity, right? So you have to be careful with it. Okay, now going to Candace's question. How would you answer number one? List the steps of the scientific method discussed in class. I didn't say here discussed in class, but I told you in class, these are the ones I want you to learn.
I think it said like traditional. Like class.
So for this, how do you explain it? You can't,
Show your work.
the teacher said this, the teacher said this. That's not useful, right? And so for this, you just list out the steps. So yes, I said for everything you have to have an explanation. For this, there's really not a way of explaining other than these are the steps, as given by the teacher that we are going to have to replicate on exam 1 and the final exam as well. Okay, does everybody understand that?
Mhm.
And I assume you're going on to another question.
No, I was just gonna clarify, like when it said classic steps, I guess I thought the ones that were listed in the book, and then we discussed the ones that you go off of.
Yeah. The ones in the book, I like the fact that he says there's lots of variations on this. The ones in the book I don't like for the reason that it looks like the scientific process ends in the way he lists it. Like you go through and you test a prediction, and then you said you come to a conclusion or something like that. You do come to some conclusions, but the process doesn't end there. You come to a conclusion, well, I have more confidence. Is that a conclusion? Not really. It's just building up your confidence. And so that's the big difference between the two, is to make sure that it's clear that the process isn't over after you've tested one prediction.
But is that not the classic one?
They're,
Just going off the word.
well, going off the wording, as the textbook says, there is no classic one, so to speak.
So you prefer the one that you share?
I do, yes.
Okay, perfect.
And you can always look it up on the lecture slides, right?
Yeah.
Okay, Skyla, did you have a question on another homework question? No, okay. I saw your hand up. Okay, given that we're halfway through the lecture, I'm going to move on. And I'm not sure why I have a blank page. Oh, that blank page is your first clicker question. It was just trying to be sly. So remember, it's session ID is WebFizz, or the channel number is 33. Oh, and I still haven't updated it, so I still can't tell you what your status is, Casey.
Oh, I paid for it. I just gave up. So it's fine. They have a rebate thing. I'll get like 17 back after I pay for because you have to mail the thing to the company.
Okay, we still have 6 more people.
I'm not told. I don't know how to.
How to what?
I don't know how to work the clicker.
Okay.
Depends on how heavy the box is.
Yeah, this one might be wrong.
I'm trying to figure it out myself.
No, I'm sure about it.
Lecture slides as PDF. Wow, this is really helpful. Do you have an intro
It was in the first one, the prologue thing. Okay, moving on. We have 14 people, 2 people I don't have answers from. But we have of those 14 people, we had, that's in,
Mine says not accepting it.
oh, I just ended it. Did it say before I said that? Okay, so there's how we broke down. Okay, since we have the president-elect being inaugurated, it's always important to make sure people understand the difference between a majority and a plurality. Majority means more than 50%. 7 is not a majority here, is it? Nope. It's a plurality. And for political office in general, you have to get a majority, not just plurality. And with the election, you have to get a majority, not a plurality of the actual electoral votes, the ones that come from the Electoral College, because we have a representative democracy, or democratic republic, democratic republic, which means that we freely vote on who we want to represent us and cast our vote for president. And we freely vote. Person I voted for, which was the Libertarian candidate, Johnson, did not get any votes. Yeah, right. Brandon and I, if it was up to us, we'd have all different. Okay, so we got our questions here. No clear answer. Talk to your neighbor about which answer you think is right and why, and then we'll come back and we will have one person who has to be sitting in the front row. Explain.
I think the answer is A.
Yeah, I could see C. More or less. Brandon, what'd you get?
I'm not really sure.
Because she's able to move on, so it's like she didn't have to. She's able to do less.
However, I don't understand anything.
I think the answer is A.
I thought the answer was A too, but I've been wrong on every single question.
Okay,
Trust yourself, Haley. On the second part.
I think it's A because if the forces are both this way, if like the force wasn't more than the friction, it wouldn't even move. The box would move. And it says that it's moving at a constant speed, right? But then again,
Okay, let's answer a second time, and then we're going to have Vanessa explain. So go ahead and answer, and this time make sure you get it in there, Raquel.
Okay. I'll answer this.
Everybody answer a second time.
How do you? Oh, we gotta redo it.
It popped back up.
Yes, it should have popped back up.
wait, you said we got you said one clicker point if you did it wrong, but we answer anyway.
You get a point whether you answer right or wrong. It's participation points.
Oh.
I feel so much better.
But I want you to think about these. I don't want you to just say, A sounds good. You know.
Okay, well,
Okay, everybody that's here has answered. So this time we had 12 and 4.
That is the majority.
Vanessa?
Okay, I think it's C because she like is pushing towards the box, and so friction is like pushing against the box to like eventually make it stop.
Well, in this case, she's going at constant speed.
Okay.
So it's not going to make
yeah,
it stop.
So she's pushing, yeah, so it's just like the natural force, like pushing against.
Okay, she's absolutely correct. Thank you.
Oh, so it is C? Not
Yes,
What? Not majority.
it's C. Another question that didn't make it into our quiz, but is part of the ones that could be on the next test, was about dynamic equilibrium.
Oh.
This is a situation of dynamic equilibrium. What does dynamic mean? It's moving. What does equilibrium mean? That it has equal forces. The net force is 0. So if she's pushing this way and it's at equilibrium, it has to be pushing back, the friction, exactly the same on the box. So the total force in the box is 0. So I am so glad that Vanessa was right.
So always when an object is moving at a constant speed, it's at 0 equilibrium.
Its net force is 0, so it's at equilibrium. Yes. Always. Now, constant velocity, we have to be clear. Speed is only how fast it's moving. Velocity also has direction. It has to be in the same direction. So if I have, like, assuming I get there later in the lecture, I'll take this and swing around in a circle. If it's at constant speed, it's still not in equilibrium because it's changing direction.
Okay, the question is.
Yes, but she's pushing it in one direction. So one-dimensional problems, you don't have to worry about the direction. Yeah, I understand.
She's pushing it up.
And in fact, the question that I was talking about that didn't make it here, that was about dynamic equilibrium, I added in words to take care of the directionality so there wasn't confusion. Raquel.
So what does less than look like?
Okay, so if the force of friction was less than net least push, assuming it's still the same direction, which I mean, of course it would have to be, then because she has a bigger force in one direction than the force opposing, the box is going to increase in speed. Yes, Casey.
But if her force is never ever more than the friction, why would the box even move to begin with? Wouldn't she have
Yes,
to-
I heard you saying that in your discussion here. On the other hand, and she had to push more than friction to get it started.
to get it started.
And in fact, remember,
But once she's at the constant speed,
Yes.
then it's equal.
Right.
Because she's already in motion.
Yeah.
So I
So-
was right, but not in the right. That was
yes,
right and wrong.
yes.
Yeah.
To get it started, you're going to have to push more than the force of friction to get it going. And remember, the static friction, how does that compare to the kinetic friction? If you have this book, how does the force required to start it moving compare to the force required to keep it moving?
You'd have to have more initially, right?
You have to have more because you have a higher static friction. Because of that conformation, things fitting down into each other. Once it's sliding, they get up and you don't have that anymore. So the friction is always bigger when it's not sliding than it is when it's sliding. So she would have to push even bigger because she has to overcome the static friction, not the kinetic friction. Okay, acceleration. Remember I talked about Galileo did his experiments on inclined planes. And he found that the steeper it was, the greater the acceleration of the ball. What does acceleration mean?
The rate or velocity change.
The rate of the change in velocity. That's the perfect words. The rate of the change in velocity. So how quickly it changes speed or how quickly it changes direction. In this case, it was one direction. It's how quickly it changes speed. And so the steeper it was, the bigger the acceleration. And so that was his beginning to understanding of this motion. Then we have the idea of free fall. Oh goodness, here's my demonstration. I got the coin in there, nobody took it. Don't want somebody to take my quarter. If I take this ball and I drop it, what's going to happen to its speed once it leaves my hand?
Increase.
Okay, the speed is going to increase, it's going to accelerate. What happens to the acceleration once it leaves my hand?
Increase.
There's a real world answer and there's a physics class answer, but neither of them are increased provided that we specify from the instant after I let go.
Oh.
Not from before I let go to after I let
So
go.
this is basically the same thing before. So like it has to like increase initially and then it's constant when it falls.
Well, what's the acceleration right now? 0. Well, right now it's 0. And when I let go, it's going to be 9.8 meters per second
Then all
squared.
the way down it's like, yeah.
But all the way down, it's 9.8. That's the physics class answer.
Okay.
What's the real answer? The real answer is something we all have a pretty good handle on. I don't know about you. When I was a little kid and like mom's driving me from Watsonville to Santa Cruz, I'd have my hand out the window and go, like the airplane wing, going like this and feeling it push back. Anybody else do that kind of stuff? Okay, see if you're qualified to be a physicist just based on being interested in what's going on there. Right, because that's what physicists are. They're interested in how things work. So we know that there was some force acting on my hand due to that air. And in general, what direction was the force due to the air? Against me. The opposite direction my hand was going through the air. So the same is going to happen to this ball. When I drop it, it's not going to have a constant acceleration in truth because the air is going to oppose it falling. And the faster it goes, the bigger that force is, right? I can do this all day and there's not much air resistance. But when you're in a car doing 80, okay, mom never did 80. When you're in a car doing 40, the air resistance is bigger. And if you get up to 80, the air resistance is going to be 4 times bigger than the air resistance is at 40. That is, the air resistance is proportional to the speed squared. So the faster it goes, the bigger the force, which means it's going to accelerate less. Until you reach the point where the force downward from gravity is the same as the force upward due to air resistance. What do we call it when the sum of the forces is 0? Equilibrium. So then you have a dynamic equilibrium. And once you reach that point, things travel at a constant speed. Hence the ever-old question, if I climb up to the top of the Empire State Building and I flip a penny off the Empire State Building and it happens to hit somebody in the head, what's going to happen to that person? No.
I actually did do this. I really hope no one can die from that.
No. What's going to happen is they're going to say, ow! The end. Because the penny, after it's fallen a few stories, it reaches what we call terminal velocity, where the upward force due to air resistance is equal to downward force due to gravity, and it doesn't go any faster. So it's just falling at constant speed, the terminal velocity. And we can see this happening with things like skydivers, right? A skydiver jumps out of an airplane. Depending on how they position their body, they go different speeds. They say, like, if you're spread eagle, you're probably going to be somewhere in the ballpark of, 50 to 80 miles an hour. You know, if you're like this, you'll go a lot faster because you have less air resistance if you're like that. So people have survived falling out of airplanes without a parachute because, 55 miles an hour is enough to cause severe damage, but it is survivable in a lucky case. If you're skydiving, people jump out of airplanes all the time with a parachute. What's that doing? It's increasing the air resistance, and thus they follow a slower terminal velocity. Question, Candace?
Why is it that people get hurt really badly when they land in water?
Because water is hard. Water, the molecules of water have a fair amount of inertia, right? And so you hit them, and they have to move out of the way. You hit them hard, it's harder for them to move out of the way because of the inertia, and so it hurts bad. Broke my tailbone.
So if you ever happened to be falling out of an airplane, hypothetically,
Just preparing for a
and
future
you're like,
case.
yes, and you're like, wow, I totally have choice in where I'm falling. Would it be better to fall in water or like on some plush grass?
Some plush grass.
This is an actual.
Okay. Water is very hard. Your chances of surviving are really slim. I think actually landing on some bushes or something that don't have hard things that are going to puncture you is probably the safest. Obviously, nothing is safe. The actual example of this that I first read about, a guy landed like in a cabbage field.
Cabbages. So water's actually like.
And freshly plowed dirt, which is reasonably soft compared to water.
I feel like I would definitely think, man, water would probably be the best option, but now maybe not.
Yeah.
Like land.
The water's not compressible. It can only move basically outward because you can't push it downward. If you push down, it's got to come up somewhere else. And yes, it's.
What if you fell going like straight down? Like if you're standing like that kind of position.
Well, you're
Plenty of examples of that. Your back breaks and your legs break and everything else.
So another question.
Yes, we're staying totally on topic here. Haley.
If you're falling out, like would it help to give like more space? So like if you had like a coat or something and you held it.
Oh yeah.
Squirrel.
I mean,
Wait,
no, yes, like a flying squirrel. You guys have seen the I forgot what they call them, air suits or glide suits or something. And it's totally awesome. These guys dive off of a rock on top of a mountain, and then they're just sitting here with this suit gliding around. It's totally cool. They go like 5 feet off the ground. Eventually, they're going to hit the ground and die. Pretty much all of the greats have died already because you make a mistake. You know, I mean, think about it. You're on like 100 miles an hour, 5 feet from the ground.
so
There's a little gust of air. Oh! Yeah.
So you get like your jacket.
Yeah. So next time you go flying, just make sure you're wearing your trench coat. You'll be good.
Next time my flight.
Okay. Getting back on topic. So in free fall, we assume for physics class that there is no air resistance. And then something falls with a constant acceleration. We call it G for the symbol, and its value is 9.80 meters per second squared. Now, the textbook likes to approximate that number to 10 because, you know, it's so much easier to do the calculations with 10. I always go 9.8 because it's correct. So if something's falling, we actually use a little calculus to come up with an equation that says the distance it has traveled, which would be delta x, since we usually use x to denote position, is equal to the speed it had initially multiplied by time in the air plus 1/2 the acceleration multiplied by the time in the air squared. So this here is a very important equation. It's one of what we call the kinematic equations. And it tells you how distance relates to the time something is falling. Now, direction is something that's important to keep in mind with something like this. Like if I take my ball and I throw it upward, its velocity was upward, and what direction was the acceleration? Down. So I would have a positive sign for one and a negative sign for the other. The general way we do that is we assign up as positive. So generally, if I throw it up, I'd say the V initial is a positive V, but the acceleration is a negative G. And so if I treat up as positive, then I would have delta X is equal to, let's say I threw it with V initial is equal to 10 meters per second. No, 10 is too close to the G. I want to make sure we're clear on which number is which. So I put an arrow over it because I specified the direction. So if I put that in here, that would be plus 5 meters per second because it's up, T, plus 1/2, and my acceleration, because the acceleration is downward, by definition, acceleration of gravity is down, minus. And so I could find its distance it's traveled, or its position, relative starting position, at any time using that equation. Now, the equation is they've done, they said, what if we start it from rest? If I just drop it, then its initial speed is 0. That makes life easier because the first term just is zeroed out. And then I just have change in position is 1/2 acceleration times time squared. Using the textbook's approximation of 10 meters per second squared, then 1/2 of the acceleration is 5 meters per second squared. And my position would just be 5 meters per second squared multiplied by the time squared. So after 1 second, 5 meters per second squared times 1 second squared, 5 meters. After 2 seconds, I got 2 questions lined up already. After 2 seconds, 2 squared is 4. 4 times 5 is 20. So at 2 seconds here, I would have 20 meters. At 1 second, I have 5 meters. At 3 seconds, 3 squared is 9. 9 times 5 is 4. Now, the picture does not look right, does it? But if you look at the actual dots for the balls, you see the clocks are just at the wrong positions. They're actually, it's drawn right. The clocks are not matched up to the actual positions.
That's cool.
Okay, 2 questions. First, Brittany, then Casey.
I don't know if this was something I just missed, but like when measuring the acceleration, like how come when you throw the ball up, you don't, that isn't accelerating?
Well,
Or I don't know.
the instant, while it's in my hand, I'm putting a force on it. And I only have 3 minutes to get through a huge amount, which we're not going to do. You can answer this at your leisure as I'm talking about this. The time while I'm throwing it, my hand is pushing on the ball. And so the acceleration is going to be depending on the force I'm putting on it. The instant it leaves my hand, then it's what we call free fall. So free fall is when nothing's touching it, it's just gravity. And at that point, then we have the acceleration of 9.8 meters per second squared. Is that what you were asking about, Brittany?
Yes, so it's, okay, yeah, okay.
What was your question, Casey?
Oh, so most of the examples, you're just dropping something, so that's why we don't do the VI thing.
The textbook's examples, yes.
But if there's an example where you toss it up and then down, then that's what the VI thingy would be.
Yes.
But we're not using that for some of these textbook examples.
Yeah, for many of the textbook examples, it has VI 0. Okay, so our question here, we still have 5 people respond. If a falling object gains 10 meters per second each second it falls, its acceleration must be, and because we only have 1 minute left, I'm going to cut this off quickly, so answer. Okay. I don't have, well, it's because I haven't updated, I'm not sure. I think it looks like Maggie hasn't answered. And Candace has. Raquel, have you answered?
Yeah.
Okay. Oh, yes, yours is blank. Okay. And, okay, well, I'm going to go on. So we had here, those people were right. 10 meters per second, because acceleration is the change in speed per time. What's wrong with answer A?
It's not giving us a time frame.
Yeah, it doesn't have the right units, right? It's meters per second, but acceleration is meters per second squared. Okay, now this is truly the first slide from the chapter that we were supposed to finish today. I'm doing great because we are a few lectures in. This is my demonstration for inertia. Instead of having dishes, I have a quarter. Because you know what? When I screw up, I'm not going to break the quarter. So the idea of inertia that I've been talking about is that things don't change their motion instantly. The more mass it has, the more it resists that. So I have this quarter. Quarter's not a lot of mass. It's sitting on paper. What force would make, if I pull this off nice and slow, the quarter comes off, comes with the paper. What force made the quarter move with the paper? Friction. So now I'm going to do this fast. How's the friction going to compare when I do it fast versus slow? Wait, what?
It's going to be less.
Well, initially it's going to be the same. When it's stationary on the paper, it's going to be the same. If it starts to slide, then it will be less. So basically, let's say that we're going to have the same friction. But I pull it quickly, and the quarter stayed here. Why did the quarter stay there? Inertia. It's resistance to change in motion. So Newton's first law is called the law of inertia that says things stay in constant motion unless there's a force acting on it. There was a force. It did come forward some, but not enough to come out. Don't worry about answering this. I just want to get to, see, there's the example I did. This one here is like the example you have in one of the 2 options for a homework problem. The one with the toilet paper roll. If you pull it slowly, it can easily accelerate. If you pull it quickly, its resistance to changing motion makes it so you're going to break the paper. So that's how we can just pull quickly on the toilet paper and it comes off the toilet roll. Pull slowly and it unrolls. The last thing I want to get to here, Newton's second law. Newton's second law is what puts an equation to this. Newton's second law can be written as the acceleration, it is a vector, is equal to the net force divided by mass. Or you could write that as sum of the forces, because that's another way of writing net force over the mass. Our textbook, for some reason, has this written down. And you know what? That is not correct. It's not correct. It has to have the net or the summation. Because it's not a given force causes the acceleration. It's the net. It's all the forces added together. Okay, I've gone a couple minutes over, but I wanted to make sure I got to that at least. Okay, have a swell day. I'll see you for lab tomorrow. And I haven't determined what lab we'll be doing, but I will, and I'll post it on Moodle this afternoon.
Turn in one of these.
Yes, after every lecture, yes.